Hello, Matthews Gatos here. In this video, we're going to look at reciprocal, quotient, and Pythagorean identities. Let's get started. So when I talk about an identity, before something becomes an identity, we have to verify if it could be an identity. And we can do this in two different ways. One is through substitution, the other graphing. In substitution, I'm going to substitute specific values of x in place of x in the original equation to see if left side equals right side. In verifying by graphing, I'm going to graph one side of the equation in y1, the other side of the equation in y2, look in my table of values to see if they match. Now, it's important to note that one example can disprove an entire theory or identity, but a million examples cannot prove an identity because verifying does not constitute proof. It's just saying we might be onto something here. So if I want to verify this potential identity for 5 pi over 3, first thing I'm going to do is go to my unit circle and look at where 5 pi over 3 is. And that's the point right there. I know that the x coordinate is the cosine of that angle, and the y coordinate is sine of that angle. So let's look at what we have. We have cotan of 5 pi over 3 multiplied by sine of 5 pi over 3 equals to cos of 5 pi over 3. So what I want to do now is use my unit circle points. Now cotan is the ratio of cos over sine, and since the denominators are the same too, I can just do numerator of cos divided by numerator of sine multiplied by sine of the angle equals to cosine of the angle. So on the left side, I have negative root 3 and negative root 3. If I multiply and divide, those cancel each other out. I'm left with 1 over 2 equals 1 over 2. So since the left side equals to the right side, I have verified this for the point 5 pi over 3, or for the angle measure, 5 pi over 3. Let's look at how to do this graphically. To do this graphically, in y1, I would enter in cotan times sine. Now there is no cotan button, so I have to enter in 1 over tan. And I'm going to multiply that by sine. And in the y2, I'm going to put the other side, which is cosine. I'll go into my table of values for the calculator. And while I do see a whole bunch of errors, I do see that y1 equals y2 for all the permissible, that means allowed values. So that is a verification. Again, I have not proved it. We will get to proving a little bit later in the chapter. Let's talk about all these errors. Why are there errors? Well, if you think about it, cotan, which is the ratio of cos over sine, is going to have restrictions of both sine not being 0 and cos not being 0. That's why there are so many errors in there. So when we write ratios, we tend to write them in terms of sine and cosines. So the majority of the time, the restrictions will also be tied to when sine and cosine can't be 0. That's why we have errors at 0, 90, 180, 270. All the quadrantal angles are hitting an error because that's where sine and cosine both equal to 0. So we need to be familiar when sine and cosine are 0. Sine is 0. Anytime there is a factor where sine is in the denominator, there will be a restriction for x anytime sine can't equal 0. So those restrictions for sine x are the x-intercepts of sine. Now you can see on the graph there where I have my x-intercepts. It starts at 0 and the restrictions happen pi radians in both directions. So my restrictions for sine are that x cannot equal to multiples of pi, and that is definitely worth memorizing. It comes up a lot. The other one that comes up a lot is cosine. So when there's a factor of cos in the denominator, I need to look at the restrictions. The restrictions, again, are the x-intercepts. So where does cosine have x-intercepts? So I can see there on the graph that cosine starting at pi over 2 will have restrictions every pi radians in both directions. So whenever cos can't be 0, this is my restriction. X can't be pi over 2 plus multiples of pi. Again, worth memorizing. Now, occasionally, like we just saw with cotan, you're going to see restrictions where both sine and cosine can't be 0. And in that case, it's just that x cannot equal to pi over 2, multiples of pi over 2. That also is worth memorizing. Everything else in terms of my restrictions will come from the unit circle. So having that unit circle committed to memory is really important and useful, especially when it comes to your restrictions. So let's look at our first set of identities, and we're going to come up with them in general. We're going to develop them. So unit circle equation, hopefully you remember this, is x squared plus y squared equals 1. 1 because it is a unit circle. Now I also know that every point on the unit circle has coordinates of cosine theta, sine theta. So what I'm going to simply do is replace x with the x value, y with the y value, and come up with Pythagorean identity number 1. So if I have x squared plus y squared equals to 1, that will be the same as cos squared theta plus sine squared theta equals to 1. And that is Pythagorean identity, and now you know where it came from. So if I want to, I can rearrange cos squared plus sine squared equals 1, because it's always a good idea to recognize an identity in all the forms, because in a question it's not always going to appear as cos squared plus sine squared, and then you replace that with 1. So let's look at rearranging them. So in the first rearrangement, I'm going to isolate for cos squared by subtracting sine squared from both sides. So I get cos squared is equal to 1 minus sine squared. So that's another way that the Pythagorean identity can appear. So if I ever see 1 minus sine squared, I now know that's the same as cos squared. Okay, let's try that again, but this time we will isolate for sine squared. So this time I will subtract cos squared from both sides. So that's gone, and I'm left with sine squared theta equals 1 minus cos squared theta. So that is my other rearrangement. So in a question or an identity or a fraction, if I see 1 minus cos squared, I now know I can replace that with sine squared. Now let's take this Pythagorean identity and let's divide all the terms by sine squared. That's going to give us a new identity. So we'll start with Pythagorean identity number 1, cos squared plus sine squared equals 1. And let's divide every term, if I do it to every term I'm being fair, by sine squared. So here, cos squared divided by sine squared. Well, I know cos over sine is cotan, so cos squared over sine squared will be cotan squared. Plus sine squared over sine squared is 1, equals, I know 1 over sine is the same as cosecant, so 1 over sine squared would simply be would equal to cosecant squared. So this is Pythagorean identity number 2. Cotan squared plus 1 equals cosecant squared. So all I have to do, cosecant squared is already by itself, is rearrange this identity in terms of cotan squared. So to get cotan squared by itself, I simply subtract 1 from both sides, and I get the cotan squared theta is cosecant theta minus 1. So anytime I see cotan squared plus 1, I can replace it with cosecant squared. Anytime I see cosecant squared minus 1, I can replace it with cotan squared. Now let's go back to Pythagorean identity number 1, and this time we will divide all of our terms by cos squared to come up with Pythagorean identity number 3. So here I have cos squared divided by cos squared is 1. Sine over cos is the same as tan, so sine squared over cos squared would be tan squared. 1 over cos is the same as secant, so 1 over cos squared would be the same as secant squared. And that is Pythagorean identity number 3. 1 plus tan squared equals secant squared. So I want to rearrange that. It's already in terms of secant squared. Let's rearrange it so that tan squared is by itself. And I will subtract 1 from both sides and get that tan squared theta is secant squared theta minus 1. So now I know if I see tan squared plus 1, I could replace that with secant squared. Similarly, if I saw secant squared minus 1, I could replace that with tan squared. So we're going to use these identities to simplify some trigonometric fractions and expressions. So these are what we have so far. We have our quotient identities, which is tan and cotan, because those are the quotient of sine and cosine in either order. we have our reciprocal identities, our 1 over identities, and now we have our Pythagorean identities. So any one of these identities can be used to prove another identity or to simplify any trig expression. So let's talk about tips on how to simplify a trig expression. I have a couple tips. First of all, always look at your formula sheet. There might be a formula that can help you. Try to write things in terms of sine and cosine. I would say that works 80% of the time. You could factor a greatest common factor. You could combine fractions by adding or subtracting with a common denominator. Or you could multiply numerator and denominator by a conjugate. Those are some of the common ways to simplify a trig expression. But remember, no matter what method you use, you always want to look for and state your non-permissible values. Okay, let's talk about conjugate. I threw that out as one of the tips to do. What I mean by that is what we did to get rid of a rational denominator, a rational binomial. We would multiply by the conjugate, which is the same terms, opposite signs. This conjugate can be used for things that are not roots. So what we could do is if we had a minus b, we could multiply by a conjugate of a plus b and write our denominator in a different form. That one is pretty useful if you have a binomial numerator or denominator and there's nothing left for you to try. You could also, when you do that, expand just the conjugated part, leaving the non-conjugated part in factored form. So expand what you're trying to do the conjugate of, because conjugate creates a difference of squares, and it's a different way of writing that denominator or numerator. Another strategy would be to simplify trig fractions. If I have a binomial numerator and a monomial denominator, I can separate those into two fractions, but just be careful, the reverse way does not work. If you have a binomial denominator, you cannot separate that into two different fractions because there is no common denominator in that case. Okay, let's try some examples. My first one, I have cotan times cos. And I know that cotan is the ratio of cos over sine. So right away, I see a denominator, a potential for division by 0. So I always have to state my restrictions, even if the question doesn't ask me to. So I see a potential for division by 0, so I know sine cannot be 0. And this is where it's useful to memorize your x-intercepts. So that means that theta cannot be multiples of pi, because that's when the sine has its x-intercepts. So let's use our identity. I'm going to rewrite cotan as cos over sine and multiply that by cos, and I'll just put that over 1. So I have cos times cos, which is cos squared theta, all over sine times 1, which is sine theta. And there I have simplified it and stated my restrictions. Let's try another one. This one here I have cos over 1 minus sine. So it doesn't look like there's a lot to do because it's already in terms of sine and cosine. There's nothing on the formula sheet that can help you. So this is one of those examples where you can multiply the denominator by a conjugate just to see, is this going to create a new look to my fraction that might help me. So conjugate is same terms, opposite sign in the middle. Whatever I do to the bottom, I must also do to the top. So I'm doing this for the benefit of the denominator. So I'm going to leave this one factored, but I will expand my denominator. So leaving it as cos theta 1 plus sine theta. Oh, there we go, 1 plus sine theta over, now I've created a difference of squares. So I have 1 plus sine theta minus sine theta minus sine squared. And you can see my middle term is gone. So that is the same as cosine theta 1 plus sine theta all over 1 minus sine squared theta. Now hopefully you recognize that as one of my rearranged ways of writing Pythagorean identity number 1. I know that 1 minus sine squared is really just cos squared. So I will replace that with cos squared, and then I can simplify. So I have one factor of cos in the numerator that cancels with 1 in the denominator. I'm left with 1 plus sine theta over cos theta. Because my numerator is a binomial, I can simplify that a little bit further by separating them into two fractions, 1 over cos and sine over cos. I know that 1 over cos is secant and sine over cos is tangent. So my final answer would be secant theta plus tan theta. Now let's go back up here and see if I have any restrictions, because I did not state those. I do in fact have some restrictions. So I have 1 minus sine theta cannot equal 0, which means 1 cannot equal sine theta. And think about where sine theta hits 1. You can think y coordinate of a unit circle, or you could think of the graph of sine. I know that that's going to happen at pi over 2 plus multiples of the period. So there would be my restriction, and of course my final answer at the bottom there. Okay, one last one to try here. Let's look at this one here. So in this one here, secant squared minus 1 over secant squared. I know that secant is the same as 1 over cosine, so this will have restrictions anytime cos can't be 0. And I know that that happens at the x-intercepts, which are at pi over 2 plus pi n. The next intercept will be pi apart. So remember, memorize your cosine and sine restrictions. Helps make your life a little easier. So what I'm going to do to simplify this is I'm going to use that binomial numerator trick and separate it into 2 fractions. The reason that I thought of that is because I saw these secant squareds and thought, wouldn't that be nice if they could simplify? And you can see now they can. And then I have 1 minus secant squared. So the reciprocal of secant is actually cosine. So the reciprocal of secant squared would be cos squared. And of course I recognize that 1 minus cos squared is a rearrangement of Pythagorean identity number 1. So I know my final answer is sine squared. So I just want to end with one last important formula that you might want to add to your sheet, and that is not sine over cos, it is sine gerene over cos gerene, which of course is going to equal to tangerine. Make sure you guys add that one to your formula sheet. So I hope that this video helped. If it did, please give it a thumbs up and click subscribe. It helps me help more mathies just like you. Thanks for watching, and I look forward to seeing you for the next one.